What's going on, everyone? Today we're going to be talking about compound inequalities. So what is a compound inequality? A compound inequality is an inequality that combines two rather simple inequalities. So let's go ahead and let's get started by first looking at what does a compound inequality look like on an actual graph, a line graph. So here we have our first line graph that's a compound inequality. And we need to write the compound inequality for each of these graphs. Now, a lot of times compound inequalities include two words, and then the other word, or. Okay, so we'll always have one of the two in between our two inequalities. Depending on how these two are being combined, will determine which word we actually use to describe it. Here, I have an inequality, and really the way we write down compound inequalities, at least the way I do it, is I focus on one part of the inequality first, and I start off at one point. So here I'm going to look at this part of this inequality. And here I can see this is a representation of x being less than, since I have an open circle, I know it's less than and not less than or equal to. So it's just x is less than the value of -2. And now I can focus on the other inequality. Here I have x, open circle tells me it's greater than, not greater than or equal to, and since it's going to the right, again, I also know how that's greater than 1. Now when you see a space in between your two inequalities, this usually tells you that it can be one or the other. So the word that we use to describe this compound inequality is or. So x is allowed to be less than -2, or x can be greater than 1. Either value for x will satisfy this compound inequality. This is one way we can write a compound inequality, and this is one example of one type of compound inequality. Now let's look at another example. Here, rather than the two inequalities, the separate ones, pointing outwards towards each other, going in opposite directions, here it seems that we have two inequalities that we're heading towards each other. So again, I start off on one point and I try to name the equality on that point. Here it seems I had x. Since I have a shaded in circle, I know it's going to be either greater than or equal to, or less than or equal to. Since it's going in the direction of the right, I know x has to be bigger than -5. So x has to be greater than or equal to, it's allowed to equal -5, -5. Looking at the other point, I know x, again, we know it's going to be equal to because we see a shaded in circle. But here I see x actually has to be smaller than -1, so it has to be less than or equal to -1. And oftentimes when we see the two inequalities, instead of going in opposite directions, they go towards each other, we call this an and compound inequality. So we would write the word and in between, because I have this inequality and this inequality. In this case, x has to satisfy both inequalities in order for x to be true, or x give us a true statement. X has to be greater than -5, and at the same time x has to be less than -1. So only values that are in between these two numbers will work and satisfy this compound inequality. And a lot of times you'll see that this is the pattern that we have. Or inequalities will always be inequalities that face away from each other, whereas and compound inequalities will go towards each other and limit us a little bit more than or. Okay, so let's go ahead and let's continue and let's look at some more examples of compound inequalities. Here we got to solve each compound inequality and graph the solution. So these are a couple of two-step inequalities. Let's go ahead and begin by solving each one. So here I'm going to subtract 5 from each side. That'll leave me with 2x is greater than -8, since these 5's cancel out. I can then divide by 2, and I get x is greater than -4. So this is one of my inequalities that's part of my compound inequality. Now let's look at this next one. I'm going to subtract 7 from both sides. Leaving me with 4x is less than 15 minus 7 would give me 8. I can then divide by 4. And I have x less than 2. So now we want to graph this. Let's go ahead and draw a quick number line. And on this number line, I'm looking at the values. I'm concerned with what's going to happen around -4 and what's going to happen around +2. Okay? So we just graph one at a time. Here on -4, I know it's going to be an open circle, and it's going to be going in the direction to the right. X less than 2, so at 2 I'm also going to have an open circle. And now I'm going to go to the left. So I can see that the inequalities are actually going towards each other, which means that this inequality is an AND inequality. X has to be greater than -4 and x has to be less than 2. So this is the area where I can find solutions in between both these values, not including those endpoints. Again, remember those are open circles. So these are a couple examples of some compound inequalities. Now what we're going to do is we're going to look at an example that's technically it's a compound inequality problem, but at the end it doesn't look as if it were a compound inequality. Here we have this example. Okay, and we're going to solve it just like we did the last one, where I'm going through two-step inequalities. So I'm going to add 5 to both sides for this equation. I get 2x is greater than 8. I can then divide by 2 on each side. I'm left with x is greater than 4. That's one inequality. Now let's solve the other. -4x plus 7 less than -25. So I can subtract 7 from each side. I'm left with -4x. 7's cancel out. It's less than, this should get me -32. Can then divide by -4 on each side. Now remember, when you divide by a negative, when you're working with inequalities, you must flip your inequality symbol. So I'm going to flip that. -32 divided by -4. That leaves me with 8. So let's go ahead and let's graph this compound inequality. Again, we're going to draw a number line where I'm interested in what goes around number 4 and 8. So I know I'm going to have an open circle on 4, and I'm going to go to the right. I'm looking at all the numbers that are bigger than 4 for this case. For number 8, I'm also going to have an open circle, but then I'm also looking at all the values that are larger than 8. So here we have an example where both of our inequalities are pointing in the same exact direction. What we end up doing here is this allows me to write an inequality that's simply x greater than 4. Because I know x is allowed to be either greater than 4 or x has to be greater than 8. Well, if you're greater than 4, you're definitely going to be, if you're greater than 8, you're definitely going to be greater than 4. Any number that I pick that's part of this inequality is automatically included in this inequality. Okay? So any number that satisfies x greater than 8 is also going to satisfy x greater than 4. Therefore, instead of me writing both inequalities, I'm actually only having to do x greater than 4. Because any value that's part of the other inequality is already included in the inequality x greater than 4. All those values sort of overlap. So to give you a more specific example, if I'm talking about the number 9, 9 would work for this inequality because it is greater than 8. But 9 would also work for this inequality because it's greater than 4. So we can sort of ignore this part of my inequality, x greater than 8, and I only have to write x is greater than 4. Okay, and that's how this inequality works. I usually just take whichever one was the lesser, the smaller value, which in this case was 4, and it'll cover everything for both inequalities. Kind of different, but that's how this one works. And now let's look at a different example. Okay, let's go ahead and look at this one. So that's one thing that can happen when we're working with compound inequalities. Here's another example of something different that might happen to us. So here, again, I have negative x plus 1 is greater than negative 2. I can go ahead and solve this by subtracting 1 from each side. I will then get negative x is greater than negative 3. I can then divide by negative 1, and again this is going to have to cause me to flip my inequality symbol because I'm dividing by a negative. So here's one inequality. So here I get 6. I must distribute the 6. I got 6x times 2x minus 3 is greater than or equal to negative 6. So I'm going to go ahead and distribute and multiply the 6 out. That'll leave me with 12x minus 18, because 6 times 2 is 12, 6 times 3 is negative 18, all that greater than or equal to negative 6. I can then add 18 to both sides. Cancel it out on the left. Greater than or equal to. Combining these two, you get 12. I can then divide by 12. I get x greater than or equal to 1. So here are my two inequalities. Now graphing them will help me understand whether or not they're and or. Draw a line. And here I have, I'm interested in two numbers, 1 and 3. Okay. So here I see x can be, it's going to be an open circle on 3, and x can be less than 3. It's going to be all these values that are less than 3. On the other end, I have 1. It's going to be an open or a closed circle because it's also can be equal to, and it's going to be all these values that are greater than 1. And again, here we have something interesting, because x is actually allowed to be any number on the number line. X is allowed to be any number that's smaller than 3, but x is also allowed to be any number that's greater than or equal to 1. So in this problem, we aren't necessarily limited in the middle, because the value of 3 is included in this inequality. If x was to be 3, it would satisfy this inequality, because 3 is greater than or equal to 1. And I can pick any number on this number line, and we would see that x actually fits. So this is an or, although it did start to look like an and, because I had a closed circle here, because this value, because x is allowed to equal 3 and x is allowed to equal 1, we're actually able to reach any value on this number line. Any value. So this is an example. This is a special case compound inequality where we have all real numbers. There's not a single number that won't satisfy this entire inequality. This is an example where when I graph both my inequalities, the whole number line is actually part of my solution. So I hope this video on compound inequalities has helped you understand how compound inequalities work, how we solve them, and how we graph them. Like I said, there's two main ones, the and the or compound inequality. However, there are special cases in which you only end up writing one inequality and it satisfies both, like you saw in that second to last problem I did. Or there's some times where you're going to see that you draw both inequalities and you end up highlighting the whole line graph, the whole number line. When you see that, you know you're dealing with a compound inequality whose solution is all real numbers, meaning there's an infinite amount of solutions that will satisfy that compound inequality. As always, continue watching these videos, stay tuned for the next ones, and thank you all for watching.